Fluoride ions have been found to prevent tooth decay, and in some municipalities they put sodium fluoride in very low concentrations in water. Here we've got 2 millionths molar as a typical concentration. Toothpaste will end up using tin 2 fluoride or sodium monophosphate fluoride in higher concentrations, but in such a way so that you don't have much of it that's absorbed by the body. Here we've got some sodium fluoride in a goodly amount, 4/10 of a mole, and we're dissolving in 2 liters of solution. This is much higher than you'd end up having in any type of tooth preventive materials. So what's this concentration? Well, that's a simple, straightforward concentration problem where we would have moles of solute over liters of solution, and that would be a giveaway point where you'd end up having a simple division to get the molarity of the sodium fluoride. Now, this stuff dissolves completely. It's sodium fluoride here, as you can see. All sodium compounds are soluble, so it breaks up totally into sodium ions and fluoride ions. So your concentration of your fluoride ion is going to be 2/10 molar. They give you here what's called the Ka. If you had hydrofluoric acid, a relatively weak acid, it would have this ionization constant. But we're not talking about hydrogen fluoride, we're talking about its conjugate base, the fluoride ion. And if we're going to deal with the fluoride ion, we're going to have to find its Kb, because fluoride reacts with water to make a small amount of HF, very small amount, and hydroxide ions, a basic solution. If you're given a Ka, how do you find a Kb? Well, that's something that you should have memorized, and this is certainly something that you will have to use on the AP exam. The Ka, the acid, and, our Bronsted Lowry conjugate base. Here's our acid HF, and here's this corresponding base, the fluoride ion. They multiply together to produce the Kw for water. And all your problems in AP chemistry that, unless it's told otherwise, are at 25 degrees Celsius, and the Kw for water, the ionization constant for water, the way it breaks up, is a 1 times 10 to the negative 14. So if we know that the Kw is 1 times 10 to the negative 14, if we divide it by the Ka, we get the Kb. Let me pull my calculator out and see if we can do that. Here's the calculator. Now we know that the Kw is 1 times 10 to the negative 14. We get our times 10 to the negative 14, and of course we'll divide that by the Ka. Your math should be good enough to quickly do that, which is our 6.8 times 10 to the negative 4. Okay, when we divide that, we're going to get 10 to the negative 11, 10 to the negative 10. We'll see what we get. There it is. There's our answer. This is the Kb. That's a pretty important value, so I'm going to end up storing that. I'm going to store that as a very easy X. That's my Kb for the base that we're dealing with, the fluoride ion. So, okay, we're set. I'm going to enter that, and let's go back to answer the questions here. Now, we have some fluoride ion. This was the sodium fluoride that dissolved. This is what we calculated the concentration of. So we can quickly say that's going to be 2/10. This is what we have for this hydrolysis reaction, where this fluoride hydrolysis reacts with water. And it's right now in the water, we have no HF yet. And our amount of hydroxide naturally in water is 10 to the negative 14, so that's virtually 0. So we know that some of this fluoride, because this is an equilibrium reaction, notice I've got this equilibrium, and this is a really, really low Kb that we calculated, is not going to be much. It's not going to react very much. So we're going to lose a little bit of fluoride. But the important thing is we're concerned as to how much HF is being made, and most importantly, what's our hydroxide ion going to be. So at equilibrium, when things are all finished, we can say this 2/10 can be diminished by how much of this fluoride turns into HF and OH minus, and of course, our HF and OH minus are going to be here as our X's. And here we go. Our Kb is going to be equal to our products, which are the same. This is no buffer. All we're doing is letting this thing do its stuff in water. We're starting our 2/10 fluoride and see what happens. And then what do we end up having at equilibrium? So this is the equation. I'm going to do it now on the calculator and see what we get. Well, solving this might be a problem because we've got a quadratic equation. Now, you can solve a quadratic equation if you have if you're good with doing it the long way, b plus or minus square root of whatever. But I've got our calculator here that I paid some money for, so I'll end up switching over to its solver function. And as you can see, I've got things pretty well set up already. I have included the KB, the 1.47 e negative 11. And now I'm going to solve for x squared. Divide that by 0.2 minus x, exactly what we have here. So that looks good. I'm going to double check. Yeah, I've got my KB. I've got this all set up. And now I'm going to try and solve this. Presently, I've got x set up as the KB. So I'm going to get rid of that right now. I'm going to make that as 0. And this is going to look for a solution from this set of boundaries. You can get two answers for this. I only want the positive one, not the negative where the parabola intersects the x-axis. So I'm going to start off at 0, or I can make the boundary from 0 to 1e99 either way. But let me solve it and see what our x is going to be. It's going to be a small number because this is a weak base, so let's solve. Oh yeah, that is a small number, and this is my new x. This is the concentration of x that we would put into here to work to solve our problem. But not everybody's got a graphing calculator, and they don't expect you to have a graphing calculator on the AP exam. In fact, you should never ever have to deal with a quadratic equation. Instead, what you can do is do an approximation, which will always end up working. And really, that's a faster method. And I'm going to do that right now. That faster method presumes that this minus x for this 2/10 is going to be insignificant. So we could pretty much say at equilibrium, this is still going to be pretty much 2/10. It's hardly going to be changed at all. So our equation is going to be KB equals x squared divided by 2/10, which you can figure out algebraically. But probably I would say that you should have, when you get ready for the AP exam, just to remember this equation, which is the same thing. If you have a weak base and you want to find the hydroxide ion concentration, approximately, take the concentration of the weak base that you started with and multiply times the KB and takes the square root. That is a bottom line. So remember that as a fast way of doing it. And this is really going to be much faster than doing the fancy equation that you have on the using the solver. I mean, you want to do these things fast. You've only got 20 minutes for an FRQ, so let's just take that and just go second function, square root, and remember, we had our 2/10 was our concentration for a base, and we had multiply that times the KB, and remember, I had x as my KB. I see it right up there, and I'll just put that there. The TI knows you're going to be multiplying this, and we can just multiply and come up with a value, and that sort of makes sense. 2/10 times this, square root's going to be the same value, but hey, this is almost identical to the value that we had when we had our solver problem, and it's just as good. So we've got this answer, which is going to be the concentration of the hydroxide ion. So let's scroll down a bit and answer these questions that we have. When the solution has each reached equilibrium, what's our sodium ion concentration? You say, wait a second, sodium isn't up here. Yeah, that's right. Sodium was a spectator ion. Very often they'll ask you on an AP question, what's the concentration of the sodium in this arrangement? And you've gone through all this. You say, oh, how do I figure that out? Well, sodium is a spectator ion. So therefore, it doesn't change any. What you figured out for the fluoride ion here is the same as the sodium ion. It wasn't diminished at all. So spectator ions, whatever you solve for at the very beginning, you're not going to have to worry about. Now our fluoride, well, remember, we had said that the x is going to be that low value. Let me see, tenths, hundreds, thousands, 10,000s, 100,000s, 1.7 millionths molar. So when you do the subtraction, it's still going to be 2/10. The concentration of fluoride ion is going to be the same, and that's pretty typical for any weak acid base, especially when you end up having one with this high concentration. Now, what's the concentration of the HF? Well, that was the X that we solved for, and to 3 significant digits, it's that 1.71 times 10 to the negative 6, that millionths molar. That millionths molar, okay, nanomolar. And our hydroxide is going to be the same, 1.71 times 10 to the negative 6. That was our X. Now, how do we get the pH? Now, be careful. This is one where you can stumble, and usually it's the last part of the problem. And you want to miss this last part. You got to think carefully. We know that the p-values are negative logs. So I'll take the negative logarithm of my answer. So I'm going to go second function answer. That was my last answer. And then enter. Okay. It's a nice numeric value, positive, which you expect for p-values, but this is the POH. Oh, notice I blurred things out because I wanted you to figure this out yourself. Well, if it's the POH, that's not the pH. Well, just like the Ka and the Kb both turn out to be 1 times 10 to the negative 14, the POH and the pH add up to 14. So I'm just going to go 14 minus my last answer. I'm not even going to bother rounding off. And that answer button is beautiful. And here we get, and that's what we expect. We expect a slightly basic solution. Again, you'll notice my calculator here blurs out the answer, so you're going to have to try and figure this one out yourself and carry it out to the hundredths. Typically on WebAssign, they like to have to hundredths. On an AP exam, you'd carry it out to hundredths too. A nice problem with a weak base and a Ka without quadratic equations or using sulfur. This is acid-base equilibria.